Students, today I'll discuss an interesting case of molecular diffusion. It's a case of diffusion of A through stagnant non-diffusing B. And why this is interesting? Because I have taken an example where water is evaporating into air. So as you can see from the figure that air is flowing past a test tube which is filled up with water and water is evaporating into air. In case 1, the air is dry. But in case 2, the air is humid. It basically means there is an absolute humidity of air which is given. And one is supposed to find out the value of flux of water evaporating into a stream of air in these two cases. Now, as I mentioned, it's a case of diffusion of A, which is water, through a non-diffusing layer of B, which is stagnant. So let me first try to explain this. So as you can see in the figure, water is filled up to this point. Suppose this is point 1 and the mouth or the top of the test tube, let it be point 2. So between point 1 and 2, you have a stagnant layer of air film. The air is not diffusing into water, however, water is diffusing into air and hence it comes under the case of diffusion of water vapor through a non-diffusing stagnant layer of air. Now to find out the value of flux in such a scenario, one has to derive a mathematical expression. And since it's a general case of molecular diffusion coupled with convection because air is flowing past the top surface of the test tube, so convective current actually influences the molecular diffusion process. So one has to consider the generalized expression of flux coupled with molecular diffusion and convection. So let us just first derive a simple expression for it. So we know that Na is equal to minus DAB dCA over dZ plus CA over C Na plus Nb. Since air is non-diffusing, so the term Nb is going to be equal to 0. And air is non-diffusing with respect to the water. Okay. Now the expression becomes Na is equal to minus DAB dCA over dZ plus CA over C Na. Now the binary system of water vapor and air, we assume they obey or follow the ideal gas equation, and if it follows an ideal gas equation, we can make use of this expression PV equal to nRT. So P over RT is equal to N over V, which is basically equal to C. So we can use the term CA is equal to PA over RT, CB is equal to PV over RT. So we can manipulate the expression introducing different terms to bring the equation to a particular form. So we can continue with our derivation. So it's going to be Na is equal to minus DAB. CA can be replaced by PA over RT. RT is constant, so it will come out of the derivative sign. So it will be minus DAB over RT, dPA over dZ plus CA over C is nothing but PA over P Na. You can go further. Na is equal to minus DAB over RT. Now PA, you can make use of Dalton's law of partial pressure, where PA is nothing but mole fraction into total pressure. Total pressure is constant, so it can come out of the derivative sign. So P and the expression is going to be dya over dz plus p over p is nothing but ya na. So we can take this term on the left hand side, take na common, so it's going to be na is equal to 1 minus ya minus dabp over rt dya over dz. Now if we do the integration between 2 points by rearranging this equation, it is going to be na dz minus dabp over rt dya over 1 minus ya. And if you do the integration between two different points, as I have shown in the sketch, this is point 1, this is point 2. So corresponding to point 1, mole fraction is going to be ya1, corresponding to point 2, mole fraction is going to be ya2. Similarly, in this case also, let it be point 1, this is going to be point 2. So, and as the diffusion progresses, this point 1 basically will come downwards. The same thing will happen over here. So the path length increases. So it can be from the initial path length, the path length will increase as the diffusion progresses. So you can write z1 to z2, z1 to z2, and you can introduce those limits here. So z1 to z2 corresponding mole fractions are going to be ya1 to ya2, and finally if you do the integration, it is going to be na z2 minus z1 is equal to minus dab p rt natural logarithm of 1 minus ya ya1 to ya2. Okay, and there will be a negative sign, so this negative will become positive. So the final refined expression is going to be na z2 minus z1 is equal to dab, since p over rt is there, p over rt is nothing but c, concentration, so you can write it like concentration natural logarithm 1 minus ya ya1 to ya2, and final expression for flux is going to be na is equal to c dab z2 minus z1 natural logarithm of 1 minus ya2 divided by 1 minus ya1. So this is basically the final expression that we have derived, using which you can find out the flux of water in the given case. Now, as I have mentioned, in two different cases, in case 1, air is dry. So if that is dry, ya1 can be easily calculated. ya1 is nothing but partial pressure at point 1 divided by total pressure. Now this partial pressure is nothing but the vapor pressure, because at the surface, okay, at the air water interface, it will be purely water. So most of the molecules will be of water molecules. So you can easily take it to be the vapor pressure of water at point 1. Whereas in case of point 2, it will be bulk air, and negligible amount of water vapor will be present, or water vapor molecules will be present at point 2. So Ya2 can be safely taken to be equal to, assumed to be equal to 0. So Y1 you can easily find out using this expression. Ya2 is going to be equal to 0. You put these values over here. Diffusion coefficient value will be given. Path length will be known. Concentration you can always find out. And eventually you can find out the flux. However, in case 2, the air is no longer dry, but it is having humidity. Okay, suppose the humidity value is given, and let us suppose the value of humidity is around 0.05 kg water per kg dry air. Now, since humidity is mentioned in this particular case, so in this case Ya2 won't be equal to 0, because a little bit of moisture will be always present in air. So you cannot assume Ya2 value will be equal to 0. Rather, you have to calculate the value of Ya2. And how can you find out the value of Ya2? It's simple. Since you know the amount of water vapor present in air, so you can convert it into mole by dividing by the molecular weight of water, which is 18. This should be divided by the total number of moles. So 0.05 for water divided by 18, plus the remaining amount will be air. So it's going to be 0.995 divided by the molecular weight of air. So you will have a value of Ya2. Ya1 you can easily find out, as I have explained earlier. Rest of the things are known, and you can find out the value of flux. So whenever absolute humidity of air is mentioned or humidity of air is given, you have to be careful enough to find out the corresponding mole fraction using the approach I have shown, and you can find out the value of the flux of water vapor in air. I hope it helps. Thank you very much.